I'm very, very happy to be here. Again, my name is Chris Guardo. We're going to be talking about building machine learning models to predict long COVID risk in patients using genetic survey, EHR data, and a little bit of mobile device. And I'll talk about all those things, but I guess for almost all of you, I'm a stranger, so I'll talk about myself as little as I possibly can. I was a student at Belmont University until May of 2022. And during that time, I studied mathematics, computer science, and a little bit of data science. And that's towards the end of my Belmont career, I learned that data science is pretty much where my passion is. I have so much I really like to learn about data and mathematics that's just where I landed very naturally, especially in the predictive analytics world, where we're trying to predict something like a phenotype, a test result. That's where I really enjoy myself. If you think about the little like three-pronged part of data science, I'm usually right here in between math and statistics and programming. I don't have a whole lot of domain expertise, and a lot of that comes from the physicians I work with. So shortly after I graduated, I was picked up by Vanderbilt University Medical Center as a statistical analyst, and mostly because they need more people to crunch numbers. We're at a all-time high for the demand for statistical analysts and data scientists. So it's a great time to be in this room. Yeah, for sure. So that's what I've been working on. And the first project I was put on was this project itself. And that is, we have this long COVID model that's already been made, and we're trying to improve on it, which isn't a thing that we normally do. So for a little bit of context, NIH, which is, let me jump a little bit ahead. NIH, which is you
might want to minimize the pictures over there.
Yeah. Let me try that.
There you go.
There we go. Perfect. NIH, which is the National Institute for Health, has this program called All of Us Research Program. And All of Us is a big data collaborative for lots of people to put in their data, all from the same universities at the same time, and then they standardize it. And All of Us has a lot of different types of data. So not only do they have your EHR data, that's your electronic health records, those are everything that's recorded by a doctor. So in America, that's usually all the medications you're on, any diagnosis code they make, some important lab results, things like that. And then they also have a few others. So there's a big All of Us survey that everyone in All of Us takes when you're introduced to the program. And that tells you a lot about a person's lifestyle, where they're from, what type of job they have, what type of insurance they have, how often they see the doctor, as well as things that are a little bit more nuanced. So like your average pain in the last 10 days. That's all gathered in All of Us. And then they have even further data than that, because they also gather your genetics and a little bit about if you wear like any sort of mobile device like a Fitbit, they'll gather data from that to see where your health records are indicated. So quite a bit of different types of data are gathered in All of Us, but not each patient has the same. So not every patient went and put their genetic data into the database. Not everyone went and put their survey data in. And before the All of Us program really took off, there was a national COVID cohort collaborative that really came to view. And what they did in that field is they had a lot of different people from different institutions all make a predictive model for long COVID, but based only on your EHR data. So only on data that was gathered in your electronic health records. And there has been a couple of very powerful models that have come from that. Our goal in this project was to improve on one of those models by introducing new data types. Now I'm going to do the crazy thing. I'm going to go back a slide. Maybe. Oh no. 1 second. Perfect. Okay. So we're going to talk a little bit about long COVID, because I think that's a really important distinction when it came to why some of the choices we made happened. So long COVID is a very rare phenotype. So long COVID-19 is really described as a case of long COVID where you have persisting symptoms that occur after you are totally over COVID. The disease is in and out of your body. So this would be if you contracted COVID and then even up to 2 months later, you still had like a shortness of breath, or you lost part of your taste, or if your blood pressure went up in a way that kind of like spiked. It's miraculous. And that's a really important phenotype. It's something that we want to find a lot of, but it also goes very often undiagnosed. And that's for a couple of reasons. First, we didn't really understand that COVID could have a long-term side effects on your body when the pandemic first came out. It was all about finding people who had COVID, quarantining them, and just like making sure everyone survives that initial bit. It wasn't until later on in the pandemic where we started to find these cases of people that had gotten over COVID, the virus was out of their body, they were sent home, but they still had a lot of side effects that were negatively affecting their health. And then the second part is, so the NIH program, which I mentioned before, had a national COVID collaborative, and they made a lot of models on EHR to predict this very thing. But because it's only based in EHR data, there is a very big type 2 error. That is, there's a lot of people that they misidentified that had long COVID. So people who they guessed had long COVID, but actually didn't. And that becomes a little bit of a problem, because if you're thinking about a very rare thing, something that only happens in maybe 1 out of 10 COVID cases or 1 out of 100 people, but then you have like a 2% error for those that don't, you're really more often identifying people that don't even have long COVID than those that do. Your preventative measures are going to waste. It just has a really big negative impact. So by including some other data types to try to improve on our existing model, our big goal is to try to restrict that type 2 error and get a much more specific result. So our 4 sources of data come from survey data, mobile device data, genetic, and electronic health records. And there's a good thing to notice when we talk about this data, that not every patient has all of this data, and it all looks a little bit different for every patient. And we'll go into that as we talk. So for survey data, it is mostly scalar and categorical. So you have something about like, what type of health insurance do you have? What type of job do you work? And then some others like, how's your average pain been? Your sex, your gender are all captured in the survey data. And it tries to focus on things that aren't captured in other data sources, like your lifestyle, your living experiences, and other external social factors. The other thing that's really important to notice about survey data is it's got a high missing data rate, because oftentimes someone would skip a question on a survey. That doesn't really happen when you go to the doctor. They don't not check boxes. At least I hope they don't. And that becomes a separate issue when you want to apply this to a machine learning model, because if you were to just throw out everyone that skipped any questions, you'd be left with less than 10% of people that took the survey. So trying to find a way to allow that data to be inputted and find an algorithm or a method that's going to be very tolerable to those missing data points. Next is our mobile device data, and this pairs really well with the survey data. In fact, we ended up putting these into the same machine learning model, while some of the others were kept separate. So for our mobile device data, we're looking at longitudinal data based on red health metrics and sleep statistics. So basically everything that your Fitbit tells you is what's gathered from this mobile device data. So we'll get your heart rate each hour, how many steps you took each hour, whether you're asleep or not, and what stage of sleep you had each hour. But the biggest problem here is that there's different observation periods for every patient, because the study wasn't conducted by giving every patient a Fitbit back in like 2017 and telling them to wear it every second of every day till now. This is just those that had them or not. So some people got them later, some people had them earlier, some people changed in between. And if you think about people who wear their Fitbit, some people wear all of the time. Some people wear it only when they exercise, which is like the worst case, because now we just think that their like resting heart rate's like 120. And some people like only start wearing them during a certain period. And that becomes really a big trial for us, because it's like, okay, everyone has these same statistics being read, but how many of them are really accurate? And how can we measure them in a way that we can use the same data to predict for everyone when everyone's data looks a little bit different? Yeah.
Curious about the study. Where did it come from? How many people were involved? Any details you know about the study?
Ooh, good question. All of Us is a really big research program, and I'll try to leave like a link to them at the end. Maybe I'll see if I can put one in the chat for you to find out for yourself. So when it came to mobile device data, Our actual data size was restricted in a few different inclusion criteria. But All of Us is a program that just basically picks patients to be part of the program. They're all over the age of 17, and it's a huge cohort. So you're thinking of those that had like full survey data that I pulled initially, it was upwards of like 39,000. So pretty big, but it all looks a little bit different. Did you have a question? Oh, okay, perfect. Yeah, so this mobile device was a little bit crazy, but because it had such a high correlation with our survey data, we ended up finding that there's a lot of compatibility between them. So we're going to try to put those into the same model. Plus, mobile device data, because it's so messy, it might be good to put it in some sort of a model that works well with those missing values. That's why we thought these two go together very well. If there's any more questions, stop me, because I stopped seeing face a little bit ago.
How do you decide those rows and those information that is missing? Do you delete it? Or do you include? If you can repeat the question for those.
Yes. So the question was, for patients with this missing information, how do we tackle that? How do we handle that? And the answer varies a little bit based on what type of information is missing. So first I had this like exclusion criteria of like, okay, if you didn't answer at least 90% of the survey, we're just going to kick you out because there's way too many missing points. I don't have enough to predict for you. And then from there, there's a couple of different ways to handle it. Ultimately, when it comes to our test data, things that we're going to be evaluating our model on, I don't like to fill those in with something like an average, because that is a little bit neglectful of how you're presenting your model and how you're saying it's got good or bad results. So what I usually do for a survey data is I split all of the survey data, I'll talk a little bit more about this process up, into numeric outputs. And then I would give the average for someone that filled in a missing value, if it's survey data, after they met exclusion criteria. For mobile device data, instead of using it in its longitudinal form, where you had like a big string of things, whether or not you wore it for a day, what I did is I took patients with a long COVID or a COVID test, regardless of whether it was positive or negative, and I measured their average for these metrics before and their average for these metrics after. Then I kicked out some outliers, people that, only wore it when they're exercising, have resting heart rates of 140. And then after that, those metrics, because it doesn't matter if you are missing some days before or after, or in those time periods, those averages kind of take care of some of those missing values. And then basically in the rest of the data, I tried to keep them as nulls or delete them if they had missing data. But that's when we're talking about like your genetic data. So if part of your genome for some reason didn't come through when someone did a test about your genes, you're probably just a miss sample and I need to throw you out. Great question.
I'll interrupt you one more time. Question from Zoom. Where do you store, or where is the survey data in particular stored in files or database? Is it on cloud or on premises? And I guess that goes back to the
All of this platform. Yeah, great question. So that All of Us data is has a little bit of a shield, a buffer around their data, because although it's very public and all you have to do is apply for it to get it, you don't have to pay for it. They don't want people messing with that data to try to keep it very structured and to keep it from being deleted in any way. So what they do is they actually have cloud compute coupled with that data in the form of Jupyter notebooks that you can use. And then each researcher just pays for how much compute they use when they process this. So it's stored through a Google file system in their cloud. And All of Us, and then you're able to compute things there through Jupyter notebooks, SQL or Python, and pull as much information as you want. But all of this data is stored in the same location. Now, it gets a little bit crazy to compute a lot of it at a time because it's stored on the cloud and the computation is on the cloud. Those things can get a little bit hairy if you're trying to pull large amounts. So usually what you do is they've got a very good data dictionary and you look up Are there any more questions that popped up in chat?
That's all I see.
Okay, perfect. All right. So talking a little bit about genetic data, because that's where it gets crazy. Genetic data is one of those data types that doesn't want to play nicely with any other data. And you can think about this why, because if I was looking at someone's genes and someone's like electronic health records and trying to diagnose whether they were at risk of falling, your genes might have a little bit to do with your bone density, but none of them are going to weigh up to the fact that to something like your age. When you're a 2-year-old, you're going to fall all the time. And when you're older, the falling will have like bigger health effects. But regardless of your age, when you're like 20 or so, you'll probably be okay. So genetic data, it needs to be treated very separately because of how it's structured. We have a lot of variables that have very little variability between them that we're pulling. So in general, what we did here is we have sequence data from genetic variants that have been already previously identified with COVID-19. Either they were related to COVID-19 hospitalization or COVID-19 contraction. So then we took those pre-identified variants from other studies and we pulled just those genetic variants to see what patients had them. And if you had that variant, then we would try to measure its expression. And that expression, that genome data is usually measured by a 0, 1, or 2, by how often that gene is expressed. So 0 means it's never expressed, 1 means it's expressed a little bit, and 2 means it's expressed usually multiple times, depending on exactly what type of sequence you're talking about. So if you think about, we have like 27 or so genes here that only have 0, 1, or 2 as their values. We have only a few discrete outcomes for each gene, and each one contributes a little bit. But if you were to throw this at a machine learning model with a lot of features that contribute a lot, it's more likely to just ignore the genetic data because it doesn't understand where it loops in. And that's why what we did here is we actually put genetic data in its own model. And I'll talk about that process a little bit more later. Perfect. And then our last one that I'll talk about is our electronic health records. And I didn't have to do a lot of big searching on this, which was a little bit helpful, because we're actually going to start with an EHR-based model that already has a lot of things filled out for us. So NIH put out that call for predictive models, and one of them that came up was a random forest model using electronic health records. That did pretty good. And its strongest features were medications, metrics from doctor's appointments, and diagnoses codes. For those in the medical world, we were using ICD-9 codes, but basically a generalized diagnosis code for any sort of different diagnosis you can have, whether it's a flu, whether it's you broke a leg, whether it's depression. Those are all captured in ICD-9 codes as long as they're part of your medical history. So because there are strong models that already exist using this data, we're going to piggyback off of one of them. And that's because all of us data is very good, but it's not as broad based as someone that has done an electronic health record study on multiple different hospitals. So I'm going to piggyback off of someone that had better electronic health record data and use their model. Then I'm going to use all of us data to see what other data types I can fish in and pull. And the good thing about this is EHR data is relatively standardized between different medical facilities. So even though they weren't making their model on the same data we did, all of the data is still in the same system. It's in the same format. So using all of us data, I could still use the same cohort of people, which was nice.
Question.
Yeah.
The EHR data that you're working with, is it tabular or is it free text?
Ooh, good question. It is definitely tabular. So I didn't pull any like natural language processing models to search through doctor's notes or things like that, which was nice. And this is a lot of EHR data does start tabular. Usually where you get those like NLPs is when they want some additional information from doctor's notes. And we tried to stay away from that because we don't have the original data that created this model. So we don't want to try to access or add things from a model that we didn't have before.
A couple of questions on chat.
Mhm.
Really going back to the previous.
Okay.
One is on what type of devices are we looking at? Only one with data like mobile, et cetera, or it's hard for me to are some of these with multivariate variables? You're really just looking
Correct.
at Fitbit, is that correct?
That's right. So it doesn't have to be an yes. Let me repeat that so everyone can hear. My bad. I'm great at Zoom, guys. So the question was, for this mobile device data, is it all coming from the same format, the same type of device that's capturing that data, or is that multiple formats? Well, I'm glad to tell you, I didn't use your Google search history to decide whether or not you had long COVID. It all came from a Fitbit or something relatively similar. So any sort of like smartwatch, and we're only looking at steps, sleep time, average heart rate, and blood pressure. So things that are very normally captured by like a Fitbit. But that's what we consider mobile device. The only reason we say mobile device because it might not be an Apple Fitbit. It could be one of those Android smartwatches or Samsung somethings that exist.
One other question, I think I know the answer. Are you cleaning, enriching, aggregating the survey and generic data before delivering to the data science team? I think all of us kind of.
Good question. So the short answer to that is I do a lot of cleaning, but All of Us does a lot of regulating on its own, which is helpful. The data science team for this project looks a little bit different than most data science teams, because for this project, we had a group of about 7 people. I was the data science person. We had one more person that was the programmer that gathered me the data. That's about it. The good thing, All of Us data was already mostly cleaned. But I did all of the transformations that happened with this data, and she did all of the pulling and some of the like data pipelining when it comes to that. So most of it was cleaned beforehand. Like they didn't have any everything was like checked box. They made sure there weren't any like duplicate values, anything like that before it came to us. But I had to be the one to go through and change all of this data into numeric data. I had to change it from by question to by person, and all of the fun things that come with data cleaning over a long period of time. So yeah, Mitch.
Yeah, is the EHR data coming from All of Us too?
Good question. So question was, is the EHR data coming from All of Us too? The answer to that is yes, except the EHR model that I'm going to be using isn't one that was created on All of Us data. So we're going to use that All of Us data so that we can apply it to this cohort of people. But this was used by different hospitals' own EHR data. But because it's standardized, we can apply it to anyone. But All of Us does have EHR as well as the other data sources. And that's why this cohort of people is really good to test something like this on, because we have all of the data types for them.
This kind of data fit with the survey data and device data.
Yes.
Not with genetic data.
Yes. So Carlos asked, does I'm saying short answer, long answer for everything. So it's all fitted. All of the patients have some or all of these. I only included patients that at least have 2 of these different data types. So some of the people in All of Us might not have their genetic data on file, maybe don't wear a Fitbit every day. But they still have the other 2, which means we can make some predictions based on them. However, I restrained from putting them all in the same model. So not only did I keep the genetic data separate, because the EHR data had such a good model that goes with it from someone that had bigger, more widely available data than us, that's also its own model. And then I created an original model for the genetic data and for the survey data / mobile device data separately. And then I'm going to combine those models in what I think is a clever way, but very elementary later. Great questions.
There's one more question from the audience. So asking about, does the data science team have full access to sensitive data? Is it anonymized? Are there other things that you can see?
That's a great question. Here we're working with no PHI. So in the medical world, we talk about PHI as personal identifiers to who you are. And there's a big list of things that goes with it, but that is things like your name, your exact birthday, where you were born, family members, phone numbers, emails, things that someone could take and get to you. Now, because All of Us is a public data platform, they don't like to put most of that out there. So basically, they just put your age, not to the day, but just to the year on there. They take away most of the statistics about where you live, and then they replace your name with some sort of an ID number. And then internally, they have some sort of table that could take these personal ID numbers and actually find the person that they're located to, but that isn't accessible for researchers. So on this project in particular, I did not have any BHI. On some of the other projects that I do, we do have access to that. That can be helpful when we're talking about like geolocations and seeing if there's like differences between rural and urban populations, but not for this project. Perfect. All right, I'm going to go to the next. All right, perfect. So now I'm going to make a very obscure analogy with pancakes. So biomedical data is tough because every patient has different types of data, and that looks very different for each person. So the best analogy I have is like if you were making pancakes and you have blueberries and maybe honey for being healthy over here, or syrup or pancakes or chocolate chips. Those are all good things, but you're gonna have to serve a lot of different people, and you don't have blueberries for everyone. You don't have syrup for everyone. That's because not everyone's gonna have genetic data on file. Not everyone's gonna have their mobile device data. That's gonna be like the rarest thing. That's like the top shelf chocolate chips for the pancake bar. But we still need to make something that's complete for each person. So we have to be able to find a way to cater to what data they have. And a big part of that is either allowing them to have a lot of missing data, or treating each of those data types that they could have separately when doing our analysis. And that's what we'll be going into, because biomedical data is hard, especially when we want to include anything that isn't standardized. Okay, so we're going to talk about a few of the different data transformation techniques that I used. So when it comes into data cleaning, I did a little bit of the cleaning, but this is most of what I did. So for the mobile device, I actually found only patients that had a COVID test on file, regardless of whether it was positive or negative. And I measured their average before and their average after. And then that change variable ended up being our variable that we're going to use to predict our feature for our model. And the idea of this is if you see a drastic change in someone's health, is it normal to the change that normally happens over the course of 6 months or so? Or is it something that's indicative of only people that have had some sort of change after a COVID case? So a great example for this is when we first saw this data, we were just like, oh, it looks like a lot of people after testing positive for COVID have a very decreased step count each day. We did a little bit more digging, and it turns out when everyone got sent home from quarantine, everyone had a decreased step count each day. So that wasn't a very great variable just to use on its own. And that way you needed some way to compare it to the average. That's why I included people that didn't even have COVID, but they had a test. So we still had some way of measuring before and after in a time period for them. But if they tested negative for COVID, that likely means either they had some sort of other disease or they didn't have COVID at all. And now we've got some ways to standardize it. Our model has things to pull for cases and controls, which will be nice. Now for our survey data, I changed all of our categorical variables into a series of binary variables. So if one was insurance type, I would be like, do you get your insurance for work? That'd be a yes or no. The next one would be like, do you buy your own insurance? Yes or no. Are you uninsured? Yes or no. And it would just be a big series of binary variables for anything categorical. And then I'd change any options that already showed discrete steps into scalar variables. So if it was rate your pain on a little bit, none at all, a lot, or I really should go see a doctor as their steps, then I would try to change that to like a 1 through 4. And then I created a function to fill in missing values for our survey data. I think I spoke about this a little bit. And that is for anything that is scalar or categorical, I would take the average. And that does feel a little bit weird. So if you don't have someone's like insurance type, I would be filling in the average insurance type for them. So they'd get like a 0.17 on every category, which is weird, but at least gives our model something to go off of. And I think that's going to be really important for any survey data that we include in a model that can't handle those null values. And like I said, I only did this for the training data, just to preserve as much as I could for the training data. And then our test data cohort for this turned out to be the small population that really did fill out the entire survey, has no missing genetic data in these things. So a couple of initial assumptions. The first assumption is that we have our data variables are not independent of each other. They're actually quite separate, but they have a lot of interactions that correlate with each other. So if you think you have a gene that puts you at risk for heart disease, you might also have heart disease in your EHR history. So they're not independent, but they are separate. So we have to find some way that doesn't require independence to measure them differently. And then the second assumption, the thing that kind of bases this whole experiment on, is adding more data types should increase our accuracy of our overall prediction. So we have a pretty good prediction based only on your electronic health records. We want to increase that a lot once we pull different data types. All right, one more story time, because I can't get enough of them. And this one has a little bit to do with parenting. So do we have any parents in the room? Perfect. Okay, a few. Have you ever lied to your kids? Yes, I get a lot of nods. I think it's kind of weird if you don't. So my mom lied to me once and I never let go of it. And what she did is I was maybe 4, 5, 6, and I hated brushing my teeth. But sometimes it's hard to reason with the 6-year-old about like the vast consequences of brushing your teeth. So what she told me instead was that it was a federal offense, and that I could be arrested for not brushing my teeth. You can guess what I did after that. I brushed my teeth a lot. And it was a lie, very blatant. But the good thing is it got me to come to the right conclusion, even if I didn't know all the steps in between. And this is what I'm going to do to my babies, which are machine learning models, is I'm going to lie to them because I want them to draw to a conclusion that they might not have all the data or perspective for. So if they don't have all the data or perspective for tackling exactly specifying what is a long COVID case, especially because these are often misdiagnosed. It's a very, very rare phenotype already. I'm going to tell it that some of them have long COVID that actually don't when it comes to training data, to try to lead them on the right path. And then once they kind of take some conclusions for themselves, I'm going to take that away when I actually test how these models do. So the simplifying assumption that I made there is I took our original EHR model, and that random forest model was trained on data that wasn't ours and was very extensive. And it gave a sort of probability output. And if that probability output was greater than 90%, I pretended like that person had long COVID regardless of whether or not they did. And the reason is because now that I give that data to the rest of the models to train, which have less data to use to make those original assumptions, they're going to be able to pick up on patterns a lot better from kind of the intuition of a bigger and better model. And then from then, they'll pick up on some patterns and they can apply it to what they all see. And then I'll test, when I test them, of course, I take that away because that's a little bit dishonest to just say like, hey, it works really well and the data that I like lied changed. So then I'm training these models. I ended up with 3 different models. One had survey data and mobile device data together. And because survey data had a lot of missing values and mobile device data is different for every person, what it ended up doing is using a XGBoost tree. So XGBoost stands for extreme gradient boosting. It is trees that are linked together in a way. And the biggest thing is that if they have a missing value, the tree has a way to kind of skip that step and go on. And that's really helpful because that means like some of those like survey data problems that I was talking about, I didn't have to replace as many values as I wanted to. For that mobile device data, if someone like really didn't wear their Fitbit very much before, but we had some good after, I could still put their data in and then we'd have something of consequence. And then the other thing is when it came down to like the small narrow population that wore a mobile device for the time, that was about like 500 people. When we're talking about people that took the survey, that was about like 39,000 people. So those are kind of vastly different, but it could tackle both and find some interactions between. But if someone didn't have mobile device data, it would just kind of skip that part and keep going in their model. That's a really good type of model to use if you have missing data. Good.
I want to go back to lying to your models.
Oh, yeah, I like that.
I'm curious where that idea came from. Is that something you've seen in other literature, or is that a brilliance of Chris Guardo? Where did you come up with that idea, or who and how did that arise?
Well, I wouldn't call it brilliance, but that original idea came from me and my team a little bit, because especially when the first round of data came in. Since then, we've had a lot more updated data. We have a lot more true COVID controls. But when we wanted to first start exploring with this data, we got data from All of Us, and there were about 30 or so people that actually had like a long COVID case in their EHR. And that's just so small. You can't really make any predictions on that. But from other hospitals, we had this really good data model. And we were like, well, maybe we can try to find some conclusions there. Since then, I mean, there are things that exist in literature similar to this. I'm not sure if anyone knows of like bootstrapping and like different ways to try to artificially increase your data count to run models. So those are similar, but the idea for the exact lie to tell the models came from us.
Thanks.
Perfect. Let me see where I am. Oh, okay, a little bit more on model training. So I talked about the survey data model and the mobile device. Then for our genetic data, that turned into a very small neural network. So we have about 27 different genetic variables. They all have a little bit of variance, and those make for very easy splits in something like a neural network or a random forest. So we definitely went with that. And the other thing with the neural network is it usually does pretty terribly if you have missing values. It doesn't know how to handle that. But for our genetic data, that's pretty rare, because it's not very often that we go through the task of like finding your genes and like computing your whole genome down to like a binary variable basis and then somehow have something missing. So that works really well. And then again, our EHR based data model, that was a random forest that was made from someone else with much better data. I'm going to be borrowing that model and then adding some things on top of it. So now how do we evaluate this? Because we have 3 different models. They're working all independently. And I want to have some sort of way to combine those results. And what I'm really looking for is this is a classification problem overall. Of course, I might have it give us some sort of like scalar output between 0 and 1 on like how sure it is that you have COVID. But ultimately, like I want to figure out, do you have COVID or do you have long COVID or do you not? So when it comes to things I used to evaluate, we're going to be talking about type 1, type 2 error, specificity, things like that, accuracy overall. And specifically, we're going to try to narrow down type 2 error. Now, how we're going to combine these predictions is using this sort of predictive method that we came up with. It's basically a weighted average, but it also lets you put more emphasis on one model than the other, and it gives you another way to kind of tweak your prediction. So first, we're going to assign each predictive model a coefficient, and the sum of all of the coefficients is going to be 1. And then the overall classification result will be by taking each model's prediction. Now, each model is going to give us, again, a % prediction. We're going to multiply it by its weight, and then we're going to add them all together. And that's going to be our overall prediction. So the example I have here is if I gave like 50% over the overall weight to our EHR model, and then 30% to our survey, and 20% to our genetic, I'd add all of those parts together, multiplied by their coefficients, and then I'd get some sort of output between 0 and 1. And depending on where I choose to put the cutoff, like if I say, okay, if it's above 0.5, then their control, it's below 0.5, then their case, then I would use that for overall prediction. Questions on that bit? Yeah, I thought there would be some. I will start with Rohit.
How did you come up with those weights? And for someone with like missing type of data, do you just say, for example, someone just had EHR and survey, would you just take those weights and just divide that by 0.8?
Pretty much. So the question was, how do you find the weights to apply to each model? And then further on that, what would you do if someone's missing a type, one of these types of data? So to find the different weights, this is an example. This is not quite what it turned out to be. But what I do is I actually do like an iterative process. So this is why you need multiple evaluation sets. So I had one evaluation cohort, I changed not at all, I set aside for later. And then I had a second one, like maybe a preliminary test. And that's what I used to try to figure out these weights. So after I trained each of the models independently, then I would kind of iterate through a process and try lots and lots of different weights for each one. So I basically tried all different weights to the to 1/10. So I would try 0.1, 0.2, 0.3, 0.4, 0.5, all the way up to 0.9 for each model's weight. And then from there, when I found the best of that, I had to iterate a little bit smaller. So it came out to like the nearest 100th of whatever weight gave the best results.
So it's sort of like a grid search.
Yep, basically. So just like another looping process to try to find what weights would come up with the best results or overall prediction. And that best result was measured in specificity. Because again, we're trying to restrict the number of type 2 errors.
There's a question actually on the genetic data. That
Okay.
I had to actually Google before I could ask you. A question about how did you choose your SNPs?
Oh, SNPs.
Yeah, so
Mhm.
what, single nucleotide polymorphism?
Yes.
Right, okay. Google's a wonderful thing. Yes,
Right.
So anyway, you have a.
Great question. So how I chose the difference. So the question was, how did I choose my different genetic variables to go on? We call them genetic variants or SNPs, SNPs, and the way I chose those actually was I just looked at existing literature. So I found about 27 that have been identified in other research groups to be related in some way to either someone being hospitalized for COVID or someone contracting COVID, like having a COVID diagnosis in those EHR. And then I use those SNPs or those variants as my features. So looking at existing literature to see, okay, what's related to COVID in any sense? Those are the ones I'm going to use to try to predict long COVID. And that's just to really kind of limit how many genes we look at. Some people do like whole genome sequencing where they look at your entire list of genes for every person, but the compute time on that is a nightmare, especially when you're looking at cloud compute. So I just looked at 27 that had been identified from other places. If you can tell, a lot of this research comes from taking something someone else already did, stealing it, adding a little sprinkle of something of my own, and then like putting it out to make it a little bit better.
Is that how you identified, because you said for the EHR based predictions, you use the ICD codes. Is that how you picked those, or do you use some kind of variable selection for that?
Great question. Those ICD codes were pre-selected in our EHR model that was created by someone else. But yes, in the same way, that was established from someone's existing literature. And they were the ones that created our EHR model, that random forest model. So I borrowed that model and now I'm sprinkling a couple of other things, but anything they use as a feature in their random forest model was the same EHR data I pulled to run that model again.
Okay. And did you directly use the ICD codes or use the P codes?
Good question. I believe our end result was ICD codes, but it was only a few. It wasn't everyone.
Thanks.
No problem.
There's another
Any
question
questions?
that you got. I want you to finish this, but
Okay.
so I keep interrupting this. But I think you may come to later. What techniques do you use to compare your experiences, like visualizations, reports?
Yes.
Yeah.
Great question. I'm going to come to that a little bit later. If I don't answer that in full, ask me again. What's up, bro?
Can you repeat a little bit about the prediction was my understanding is it's not a binary classification 0 or 1, but is instead a probability.
Yes.
So how do you choose the threshold or you choose?
Great question. So the question is, we have this sort of prediction here that we're talking about, and the output from every model is going to be a probability. So where do we choose the cutoff to decide, okay, well, everyone that's that's got like probability over 0.75, they're definitely in control, or they're definitely a case, they definitely have long COVID, or anyone under that. So where do I choose the cutoff? Kind of the great answer to that is I started with kind of a baseline cutoff, and that was 0.5, right in the middle, to train all the models. Afterwards, clinicians will often take this and run it a lot of different ways to choose where the best cutoff is. At the end, you'll see some AURC curves, which is something that medical researchers use a lot to show the relationship of where you put the cutoff to like what proportion of cases are you capturing versus like what proportion of people are you misidentifying as having that trait. Does it help you a little bit? Yes. Okay. Cool. Any other questions? So speaking of that curve, here's some of the results. And this is just a little bit of the ways I visualize the data. I definitely use a lot of other things that were not shown here. One, because the publication for this is still being submitted. So I don't want to like spoil it for you guys, especially when we want to try to, make money and apply it to different things. But here is an AURC curve. So we have two different axes. You have your sensitivity. This is how many of the people with long COVID are you correctly identifying that have long COVID? And then you have your specificity. Like, okay, so what proportion of people did you say have long COVID that actually don't? And then you get these different curves. And generally the curves that go the highest, that sit on top of the rest, are going to be the ones that are doing the best. Because that means you're maximizing the amount of people that correctly have the condition per the amount of people you're misidentifying. And that's how we kind of weigh these results. So you can tell some of these data types on their own did very poorly. 0.5 is basically random. So the genetic data classifier on its own was not really much better than randomly guessing whether or not you had long COVID. And that makes a lot of sense because if you're only looking at someone's genes, you don't really have a lot of context for whether or not they have long COVID, because you don't have a lot of statistics for whether or not they contracted the disease or how old they are, how much those genes might actually play a part. And then similar to survey, you got a little bit better. EHR was really good. And our idea was, how can we just add to EHR? So when we combine the other two for it, genetic and survey data, we get this final curve, that purple curve, that sits on top of the EHR curve most of the time, has a better rate of change overall, which just means, hey, this curve, this prediction method has improved on our regular EHR method in most cases. And you can kind of see this gives you some sort of an indicator on where the cutoff is. Because if you were to look at like where your x-axis is 0.2, it's like, okay, where I've cut it off to a sense that I'm only getting 20% of misidentified cases. And then how many are you correctly identifying from that?
Were you able, for specific data types, like survey, there's like several, there's like the wearables, there's that was the gradient boosting model, right?
That's right. So
were you able to extract like the feature importance, like what features were the most important amongst the survey data types?
Yeah, great question. So the question is, of let's say the survey-based model, that's SG Boost, was I able to pull out some of the most important features, the features that led most strongly to the correct prediction? And there's one very boring answer part of that, which is I can't show all of them because this publication is still in the works. So we're trying to kind of keep some of those cards close to our chest so someone doesn't, I guess, like sneak out and like do the same thing as us and then find a way to publish it like in a week. But there are some things that we saw that were like very, very powerful. I think when it came to like single questions that were very powerful, questions that had to do something about your income or where or what setting you have lived in, like an apartment and a house, actually had like a pretty good result. And that might have to do with how likely you are to contract COVID just from external surroundings. And then when it came to types of questions about your overall health and lifestyle had a very big contribution. And that would be like, how do you feel on a day-to-day average? Now, none of those questions singularly had a great contribution, but when you take the sum of all the different ways on how you feel on average, it really helps to identify, hey, you've got some different different things from a COVID case that are carrying over into your daily life. Yeah.
I sort of asked this earlier, but like, for like the wearables, like, what kind of like signal processing, did you do signal processing to analyze that data?
Ooh, for some reason that terminology isn't hitting me. Can you like describe signal processing differently?
Just like, you have like, I don't know, heart rates for for a specific time duration. Like, how would you go about like, I guess, processing that? Or
Oh, yeah, cleaning and transforming that original data. Okay. So question is like, what process did I go through, like cleaning and transforming the original data? I think I've mentioned some things, but I'll try to point out a couple more. So for something like our mobile device data, I had to take something that was longitudinal, meaning you have different checkpoints in time that we're measuring this thing. And I took it with some averaging metrics. So I averaged it before and after. And then there's a certain time period in the middle that I didn't take the data from. And that would be like 7 days before you had a COVID test up to a month after. And the reason I did that is I want to see not just short-term effects of COVID, but what was your life like before COVID ever entered the picture? What was your life like after COVID entered the picture? And what does that look like differently for each person? That's some of the transformations I did for the mobile device data, was to just take those separately and then do an average for every metric.
Can you look at the variance?
We did look at the variance a little bit, and that was mostly for exclusion criteria. Because if someone had a huge variance or super, super low variance, it showed that they weren't wearing their mobile device enough to really get a take. So if they had a super, super low variance, that usually meant they only wore it while doing one thing. And if they had a super high variance, then they were just all over the place. It's kind of hard to gather. Mitch.
Yeah, so then for the before and after, you're setting some kind of statistically significant threshold to measure that? Or?
Good question. So the question was for the before and after case with our mobile device data, was I setting like a statistically significant threshold? And the answer to that started as a yes, and then it turned out to be like a little bit of adjustment after that as well. So anything that was considered an outlier in variance or average value, I cut out. So if someone was an outlier for their average value, that usually meant their resting heart rate was way too low. That one was very rare, or way too high when I averaged it to make any sense. And for those, that was mostly people that, like I said, just wore it during exercise, because then your heart rate appears to be much higher than it actually is. And then I did the same thing for the standard deviation variance to see, okay, like, are there some differences here as well? Are you someone that are just doing too many things with your mobile device on for me to really understand what your daily life looks like?
Another question, so do you know why the combined data classifier has more sensitivity than others?
Oh, good question. So question was, do I have an idea why the combined data classifier has more sensitivity than others? Well, I like to think it's because I did a good job. But the combined data has a lot more information than the others, because the combined data is taking the result from your genetic, your survey, and your EHR, it's scaling them together and putting them out for an overall result. And I want that to be the best, because we're trying to improve on the data from just the prediction that only comes from one data source. And by doing that, by combining those different data types, it's telling a bigger story about who you are and why you may or may not have long COVID.
To follow up on that, did you take pairs rather than all three? In other words, the genetic is almost 50-50. Did you take the other two and did you get similar results?
Good question. So the question is, did I take pairs of these? Like, did I make a predictive outcome with just maybe genetic and EHR data or genetic and survey data? The answer is yes. I didn't include them all here, mostly because that gets to be a very messy graph when you've got like 7 different graphs all layered on top of each other. And it was a relatively similar result. The biggest thing is EHR, the prediction got a lot better when you combined EHR with something else, because EHR tells most of the story. That's all of your medical records. We'd hope that's the most relevant to what's happening for you medically. But then when you added something to it, it got a little bit better because now it knows a little bit more about something that might contribute that wasn't captured in just your medical history. But if you took like survey and genetic data and added them together, it doesn't really have enough context to make much improvement.
But for instance, I'm sorry to talk to you, but survey and each EHR, those two together weren't as good as all three.
That's right. Mhm. Awesome. So getting up to the last slide here, a little bit of research implications. And the first one is very general, and it's that you can combine different data types using independent models, and it does lead to overall accuracy. That's kind of nice. And it opens the door for other types of problems in data science, where you have different data that doesn't play nicely together. You might be able to run them separately and still improve an existing model's result with some increased accuracy from combining different data sources. And that's something I'm interested to see where we can apply it, because of course it's going to be very applicable to genetic data and the EHR data for as long as those two exist. But how else we can apply that when you have different types of data? Another point to make on that is we made some sort of method that works for no matter what type of data you have. So no matter what type of data you have available, we can still feed it to this method and it'll spit out a result. And that's really nice. And of course, the more types of data you have, the better your result is. That's good. And the last thing is long COVID-19 risk can be predicted with multiple data sources with improved accuracy, which is really helpful just for us in the medical field to see what do we want to look for overall when looking at long COVID diagnosis. Thank you. That's about up to the end of my presentation. I'm happy to answer any more questions before we go.
Yeah, let's.
I'm just curious why
Is that good?
yeah, why do you decide to go for edge boost and neural network specifically genetic data, but why no a neural network for all 3 kinds of data?
Ooh, good question. So Carlos asked why, he's curious why I chose to do like XGBoost for our survey data and mobile device data and neural network for our genetic data, and not just a neural network for everything. This is a great question, actually. Neural networks are very, very strong, but they're also very dependent on some things. So the biggest thing with neural networks is like they're the basis of deep learning. They basically anything that your brain can come up with, ideally a neural network could come up with given enough data and time, right? But the biggest problem with neural network is it takes a lot of data to really well train a neural network. And then the second is it does not do well with missing data unless you add something else to it. And that's the real reason I didn't use it for our survey data and our mobile device data when I wanted to combine those, because only, let's say, like less than 10% of people in that cohort actually had full mobile device data and survey data. So if you had any missing value, the neural network doesn't know what to do with them. It can't train with them. And that just brings the training value down really small. And then if you take that cohort that's really small and give it to a neural network, it doesn't have enough iterations to really make sense of it. Especially with something that's already rare, like a phenotype that only occurs out of like maybe 1 out of 10 people with COVID. And because of that, neural network just didn't fit that scenario. I think neural networks are super strong. If you can get enough data of something, you can probably get a neural network model that outperforms almost every other model. And if you have enough time, you can make a deep learning model that outperforms that one too. But I didn't have the data really to support that infrastructure.
Actually, I just saw up here, someone didn't put it on chat, but it's raised their hand.
Oh.
Sassy.
Sassy.
Hey, hi. I have a question like this was an earlier question which you said about data types. Which did you classify while classifying it? Did you label any of the data to categorizing some of those things? Because when it comes to a Fitbit or something, some people will be doing a lot of exercise daily. Some people doesn't do. Is there any variations about the age factor? Like about a like workout freak? So identifying those things, labeling those.
Gotcha. Okay. So did I use some of that internal data to identify as like if you wore a Fitbit, how much were you maybe exercising? Does that have to do with things like your age? And the answer is I didn't do a lot of internal investigation there. I did mostly just cleaning and then feeding it to a model to predict. There are definitely some factors there. So I think like originally we did find that just before and after during any period of time, someone's average steps goes down and average sleep goes up. That could be because they get older. But most of these cases, I was only over the course of a year. So to me, it's more likely, hey, just over the course of a year in the last few years, most of us take less steps and sleep more because we're working from home more. This was also data gathered mostly during the pandemic when you have people that actually have COVID tests in their like medical records. And because of that, like we ended up finding some things there that we weren't necessarily looking for, just to find out, hey, everyone's steps and how much they sleep has changed a good bit over the last couple of years. But I didn't do any of that like internal identifying. No.
One more question, like is the survey includes a food criteria or something?
Can you say that one more time for me?
Is the survey or do you have a survey data which includes any food criteria?
Ooh, okay. So do I have a survey data and does that include any, what was the last part?
Food, eating a food or something.
Oh, like dietary
Right,
criteria.
yes.
Nutrition criteria. And only one way. One of our survey data questions talked about food insecurity. So that is how likely are you to like be able to obtain your next meal? Like, are you worried about where your next meal will come from? So that was there. And that's a little bit more on maybe like a poverty side of things when we're talking about food insecurity. And we didn't have a lot of nutritional data in our survey. It would be really interesting to see because I'm guessing what you eat has an impact on your health, or at least my mom
Is it in a variable selection? It's an important factor for considering it. Like, did you got any features while feature selection? Is it a major factor for that?
Ooh, so is food insecurity a major factor when it comes to feature selection? It wasn't in the top 10. And it does kind of go with overall health. So it was in that category that came out more than the rest, but it wasn't in the top 10 of the features of our survey that had the most contribution. Now, our survey was like 80 questions or so. So it was a pretty extensive survey, but it wasn't in like the top 1/8 of it.
Well, that's last question. Sorry. How many variables you had at last when you combine all those things?
Ooh, so what features were most important when we combined all those things?
Yes.
Okay. I'll try not to spoil too much because we have a publication coming out and I don't want to get myself in trouble, but I've got some that I can tell you about. So some of the variants that had to do with COVID-19 hospitalization, those are genetic variants, did better than variants that had to do with just whether or not you contracted COVID. And that kind of makes sense because it's bringing up more severe cases. I talked a little bit about the survey data overall, things that had to do with like income and your housing were really important, as well as any overall health. And then when it came to mobile device data, it was give or take. The mobile device data was a nice sprinkle on top, but none of them were very big heavy hitters. And for our EHR model, you can actually look this up. I should probably.
I didn't have a SHAP. I was expecting a SHAP values.
Right. Don't have those SHAP values for you right now.
Okay.
But in our EHR model, you can see its biggest features, and a lot of them are like medications and prior diagnoses.
Thank you. Thank you so much.
No problem.
So on this slide, one of your last things, the first bullet point actually seems to be what is really unique about this. I'm wondering how unique that is, as far as using independent models and then weighting them like you guys did.
Great question. I think the exact weighting system that we did is more unique, but lots of people are trying to combine different data types, and how to do that is a little tough. The best way I've seen so far in a lot of modern literature, and most of how I read is very exclusive to biomedical and informatics. So talking about in the medical world and phenotyping, but some of the best ways I've seen to combine different data types is using a deep learning network. And that's not only when all of those data is widely available, but deep learning is like it feels like the opposite of almost every other machine learning because it is so hands-on. Like you are designing some of these layers of this model very specifically so that you can handle something that's input might be like a matrix versus something that's input might be like a color or a shade. And those deep learning models combine different types of data very well. So I think that's kind of like the maybe gold standard for how to combine different data types. And this is more of an elementary one, but it seemed to produce some good results.
Other questions?
Just quick question.
Mhm.
The paper you mentioned, the reinforced EHR model
Mhm.
paper, do you happen to know the authors or the title?
Oh, it is in NIH. It was in their original call for long COVID research. I'll try to get it to you if you give me your email. I should have put it on like a final slide here, but someone forgot. So
Appreciate it.
One more time. Thank you.
thank you.